Section 4.5 is on page 255, talks about indeterminate forms and L'Hopital's rule. And this is something we're going to start playing with. 1 over 0 is either positive or negative infinity. Of course, this is with a limit. If you're approaching 0 from the right, it's positive infinity. If you're approaching 0 from the left, it's negative infinity. And 1 over plus or minus infinity is 0. Something we're going to have to play with in this section. Infinity plus any number is infinity. Infinity plus infinity is also infinity. Infinity times any positive number is infinity. And any negative number times infinity is negative infinity. Anytime we're talking about infinity, think of a very large number. Now, the cases in which we have to investigate more: infinity minus infinity, that depends. Infinity times 0, that depends. Infinity divided by infinity, that depends. And 0 over 0, that depends. Zero to the 0 is something we've been avoiding all along. Infinity to the 0, 0 to the infinity, and 1 to the infinity. Those are all indeterminate. We have to really figure out what is the answer in this section. And once you learn this section, you really have to apply it everywhere. Keep in mind, if you're talking about growth of functions, factorial is the fastest growing function, exponential is next, polynomial, radical, and the slowest growing functions are logarithms. To undo a very fast function, you need a very slow function. Those are inverses. And to undo a polynomial, you need a radical. We do not know how to undo an exponential yet. Let me remind you of the tricks of a limit back from 1140, the previous class. The limit as x approaches a of f of x. The way you find limit, a shortcut, you plug the value in. If you get an actual number, you are done. If you get a number over 0, back in the days we said does not exist. What that means, it's either positive infinity or negative infinity, one of the two. And if we got 0 over 0, then we go on. This is, of course, provided f is a radical equation. It could be, we have a list of those. F could be a radical, it could be a log, an exponential, a rational. Where they're defined, of course, trig, where they're defined, a polynomial. There is a big list. Absolute value that doesn't work on, you can't plug that in if you have an absolute value. And greatest integer function that doesn't work on, there are a few exceptions, but the majority we could pretty much do that. And L'Hopital's rule, this is what it says. It says if f and g are differentiable at a, and I take the limit as x approaches a of f of x divided by g of x. If that equals 0 over 0, or I'm adding infinity over infinity, plus or minus makes no difference, then the limit as x approaches a of f of x over g of x will equal the limit as x approaches a of f prime of x divided by g prime of x. and that's L'Hopital's rule. It's basically just that rule right there. We're going to manipulate using algebra to get this form so that we could apply L'Hopital's rule. On page 262, directions: use L'Hopital rule to evaluate the limit, then evaluate the limit using the method studied in chapter 2. So in chapter 2, the way we worked this out, we really stated, well, if I really want to take this limit, I will need to make use of the limit as x approaches 0 of sine of x over x. That's a 1. That by itself, I could have used L'Hopital. I could have said, look, that's 0 over 0. Every time I use L'Hopital, I have to put that h on the equal, so you tell me that you're using L'Hopital. And be careful with L'Hopital. It's not the quotient rule. It's the derivative of the top divided by the derivative of the bottom. So if I take a derivative of the top, that's cosine of x over 1. If I throw 0 in, cosine of 0 is 1. Here, when we did this back in the days, we wanted the denominator to match, so we said this is the limit as x approaches 0, sine of 5x over x. We multiplied top and bottom by 5, and then we said this is the limit as x approaches 0 of 5 times the limit as x approaches 0 of sine of 5x over 5x. And this is a 5, and we memorized that's a 1, and we said that's a 5. Now, it's much quicker. Now we say, well, hey, isn't that 0 over 0? By L'Hopital, that's the limit as x approaches 0 of the cosine of 5x times 5 by the chain rule over 1. If you throw 0 in, that's 1 times 5, which is 5. Here, this was a bit tougher back in the days. When we worked this out, this took some time because we knew this doesn't factor the bottom. You do get 0 over 0, which means you had to take the limit as x approaches 1, x minus 1, x squared plus x plus 1. You know 1 is a factor of that, so you had to go on the side and figure out if I take 1 into 4, 0, negative 1, negative 3, oops, too close. You drop the first number, that's a 4, that's a 3, that's a 3, that's a 0, so the denominator happened to be x minus 1 times 4x squared plus 4x plus 3, and by canceling that 0 factor out, you would simply plug the 1 in and say, look, that's what the limit is. This used to be a lot of work. That's 1 plus 1 plus 1, that's 3, 4, 8, 9, 10, 11. Right? That's how it used to be done back in the days. Now, we say, hey, forget that. This is 0 over 0, that equal by L'Hopital, the limit as x approaches 1, 3x squared over 12x minus 1. Throw the 1 in, the top is a 3, the bottom is 12 minus 1, which is 11, and you get there a lot more efficiently. And the same deal with the last problem. Whenever we had limit as x approaches infinity, we used to say divide by the highest power term of the denominator, which is x cubed, so that will be 2 over x plus 3 over x squared over 1 plus 1 over x squared plus 1. This will be 0, this will be 0, 0, and a 0, and that will be 0 over 1, which is 0. Actually, if you take in the limit as x approaches 0 of polynomials, I suggest you stick with that. Now you have an alternative. You could say that is infinity over infinity. So by L'Hopital, that's the limit as x approaches infinity of 4x plus 3 divided by 3x squared plus 1. That's still infinity over infinity. You apply L'Hopital again. You could do that as many times as it takes. The top will be 4, the bottom will be 6x, and the limit as x approaches infinity of that will be 0. That's the alternative. Now that we know this, we could say just use L'Hopital's rule wherever it applies, and I'm going to spread those out a bit. Here, if I throw a 1 in, I'll notice that a negative 1, I'll get a negative 3 plus 2, which is 0. For a negative 4 plus 1 plus 3 is a 0. So make sure you get 0 over 0, otherwise L'Hopital doesn't apply. And now, instead of factoring or doing anything like that, we say, well, look, that is 9. I'm so stuck on x, forgive me. 9t squared over 12t squared minus 1. If you throw a negative 1 in, you get a 9 over 11. And that's basically it. Clean and quick. Here, the same thing happens. We say, well, that is 0 over 0. By L'Hopital, that's the limit as t approaches, by the way, that's limit of 5 times the cosine of 5t divided by 2. That is 5 times cosine of 0 is a 1 over 2. That's 5 halves. And the next problem up is number 18. If I take the limit as x approaches negative pi over 3, that would be pi minus pi. And if you put negative pi over 3 in there, so this is negative pi plus pi, that's a 0. That will be the sine of 0, which is 0. The same deal by L'Hopital. Every time you use L'Hopital, make sure you put that h on. Theta approaches negative pi over 3. The top will be simply 3. The bottom will be the cosine of theta plus pi over 3. Substitute the negative in there. That's the cosine of negative pi over 3 plus pi over 3, which is the cosine of 0. And the cosine of 0 is 1. And there it is. A lot cleaner if it works straightforward. Same deal here. This was a problem from the previous class. Here you had to pick points. Now you say, wait a minute, if you put 0, 1 minus 1, 1 minus 1, by L'Hopital, that's the limit as x approaches 0 of 3 to the x times natural log of 3 over 2 to the x times natural log of 2. And then you say, okay, well, let's see, throw the 0 in, 3 to the 0, that's 1 times natural log of 3 over 1 times natural log of 2, and that's my limit. So those are the cases in which we didn't really apply a shortcut back in the days. And if I look at this problem, I would say, well, I'm going to change this before I start. I'm going to write this as natural log of x over natural log of 2 using change of base. Natural log of x plus 3 divided by natural log of 3. And I would say this is the limit as x approaches infinity. I'm just manipulating the problem. So this is really natural log of 3 divided by natural log of 2 times natural log of x over natural log of x plus 3. That is the limit as x approaches infinity of natural log of 3 over natural log of 2, which is a constant. Limit as x approaches infinity of natural log of x over natural log of x plus 3. The limit of the constant is the constant. That I leave alone. But here, I notice this is infinity over infinity. L'Hopital applies on that. That's the limit as x approaches infinity of 1 over x over 1 over x plus 3. That's natural log of 3 over natural log of 2 times the limit as x approaches infinity of x plus 3 over x. That is infinity over infinity. So I would say that is natural log of 3 over natural log of 2 by L'Hopital, limit as x approaches infinity of 1 over 1. That's simply natural log of 3 over natural log of 2 times 1. And that would be my answer. Now, algebra. If I have f times g, I could say that's f divided by 1 over g, Or I could say that's g divided by 1 over f. Meaning, if I have 0 times infinity, I'm talking about limits, of course, with all of those. If I have 0 times infinity, I could say that is 0 divided by 1 over infinity, and 1 over infinity we agreed is a 0. That's one case. Or I could say that is infinity over 1 over 0, and we agreed that 1 over 0 is infinity. So of course we're not talking about 0 times infinity, we really don't do that. We're talking about if I'm taking the limit of f times g, and one of those is 0 and the other is infinity, I could use algebra to manipulate the problem and proceed. So every time I use L'Hopital, I need to be looking at either of those two cases.